Just finished the. Hi, my name is Dana Golden, and we did it. We got here. It's the electricity markets section of the class. My favorite section of the class. I love this class. I love environmental economics, but my heart belongs to the electricity market, and now I get to talk about it with you. Share my passion with you. So, what is electricity? Electricity is the flow of electrical power or charge. It's a secondary energy source, meaning that it's generated from the conversion of a primary energy source, such as coal, natural gas, or solar energy. Electricity is used for powering homes, business, and industries, and driving technological advancements, and supporting essentially services like healthcare and transportation. It is a crucial resource in economies and environmental policy. You cannot have an economy without electricity. It is the modern resource that fuels the entire economy. So key features of electricity. This is probably going to be a review of physics for most of you, but it's good to have the common language. Voltage measures the electrical potential energy per unit charge, akin to the pressure driving electrons. Current is the rate at which electric charges flow, measured in amperes. Resistance is the opposition to flow of electric current, measured in ohms. Power is the rate of energy transfer, calculated as P equals IV, where I is current and V is voltage. So the unit of power is the ampere volts, but it is also measurable in watts. So the amount of power that can flow through the through a wire is inverse to the resistance in a way that I might have on the slides, but I don't think I do, due to the power law. So alternating current, AC versus direct current. AC is an electrical charge flowing periodically in reverse directions. This is the way most modern grids are set up, though we're starting to see what's called multi-terminal DC and high voltage direct current, which are things I'm very excited about. In DC's electric charge flows in one direction like batteries. Transmission losses, electricity must travel through transmission lines and experiences losses due to resistance and inefficiencies. So you can't just like ship electricity on a bus. You have to use it directly when it happens, and you lose a little bit of electricity as you ship it through the transmission lines, usually made of copper or aluminum. So here's electromagnetic induction. You have a magnet that moves into and out of a coil, generating a magnetic field operating opposite motion. So moving a magnet around a coil of water, usually the wire is copper, or a moving coil of water around a magnet pushes electrons in the wire and creates an electric current. This is very important. I'm not going to test you on it, but just know that this is at the basis of all the turbines we'll talk about, and all the power generation is this process of generating electric current by spinning something, in our case, a turbine. The only electrical source we've talked about that isn't like this is photovoltaics, which is a very specialized form of solar that's becoming very popular and doing some really cool stuff. So electricity generation using turbines. Electricity is often generated using turbines, which convert mechanical energy into electrical energy. How it works: primary energy source is used to produce mechanical energy, usually in the form of steam, which heats water. If you produce thermal energy, this produces steam. This spins the turbine, and the energy is used to spin the blades of a turbine. The turbine is connected to a generator. Inside the generator, magnets and coiled wire interact to create a flow of electrons, and this is electricity. So common types of turbines: you have the steam turbine, which uses steam produced by heating water with coal, natural gas, nuclear, or concentrated solar power. This is not the dominant way solar power works now. Obviously, that's photovoltaics. We have steam turbines, which uses steam to spin the turbines. You have wind turbines, where you harness kinetic energy of the wind to turbine the blades. You have hydroelectric turbines, which use the water to turn the blades. Obviously, dams. Another example is pump storage hydroelectric. And you have gas turbines, where you burn natural gas to produce hot gases that drive the turbines. The efficiency of electricity of generation varies by energy source, technology, and environmental considerations. So even amongst energy sources, they're not all the same. And a lot of it's driven by how this process is being done of converting the raw energy source to the electricity through the turbine. That changes the efficiency and changes the levelized cost of energy, which changes how willing you are and how valuable the energy is, how willing you are to implement the energy and how valuable it is. So why is electricity important? There is a reason we call it power. Electricity is what makes modern life possible and allows for complex transactions and action to be performed. If you've ever been in a blackout, you will notice that you will feel powerless. You feel like you can't do anything because there's no electricity. It's highly vital to modern life. Capital without energy is a statue. Labor without energy is a corpse. So the role of electricity in living standards, notice the richer a country is, the more energy they're using. So where we have poorer countries or developing countries, they're using less electricity. And then in the developed world, they use a lot of electricity per capita. Energy and electricity in particular are crucial to having good lives. What makes electricity special? Why are we talking about electricity? There's no lecture at Stony Brook that spends an hour talking about the clothing market or how you do textiles. What makes electricity special? What are the economic properties? It's difficult to store. You have to use it almost instantaneously after you develop it. The electric grid is, in many ways, the most complex project ever built by mankind, and there's so much that goes into making it work. The market must balance continuously. Also, there's a highly inelastic demand curve. Pretty much no one is who's using electricity, because most of us are retail buyers. Pretty much no one is faced with the cost of electricity in any given time. The cost of electricity for retail buyers only changes by year, and often the people who are turning on the light switch are not even the people who deal with the costs. So retail buyers are given a fixed price by the utility. So there's a highly inelastic demand curve for electricity because the retail market feeds in the wholesale market, and the retail market is inelastic because in the retail market you buy from the utility who gives you fixed costs. And there's a belief in near constant ability for reliability. We'll talk about this a lot in the capacity markets lecture, but essentially in the United States, in the Western world, we have this feeling that electricity is a right. We have this feeling that if electricity doesn't work, we will be very angry. If you look at places around the world, even in developing countries, where electricity goes out, when the power goes out, you see riots. Because you feel powerless and you become angry at who's ever in charge. In a very pertinent case, Maduro, there were riots in Venezuela over Maduro's inability to stop the blackouts. So structure the electricity market, there are three parts. There's the generation, where you produce the electricity. There's the transmission, where you send electricity long distances. And then you have the distribution. This is the last mile problem, where you're sending it to the end user. This is like the power goes off transmission line to your neighborhood and into your home. So generation, producing electricity. Electricity is generated by converting primary energy sources into electrical energy. Obviously, there's three main types of electricity generation. First off, fossil fuels. Second off, renewable. And third off, nuclear. You also, I guess, could have energy storage systems we'll talk about next lecture. But today we'll think about fossil fuels, coal, natural gas, and oil. Produces steam or hot gases to drive turbines. Wind, solar, and hydro, and geothermal harness natural processes. I'll say hydro is not, for the purpose of the science, yes, it's definitely a renewable energy. For economics, a lot of people lump nuclear and hydro together because economically they're pretty similar. Because they're both very investment intensive, and there are often limitations on how much you can build quickly, unlike solar and wind. And so heat from nuclear reactions generates steam for turbines. And then economic implications, you have to think about, when you're thinking about how valuable and how worthwhile it is to build these things, you have to think about fuel cost and availability. You have to think of environmental externalities, how to internalize those. Renewables don't generate any greenhouse gas emissions, at least when you're running them. I mean, there's some greenhouse gas emissions in producing the materials for renewables, but you have to think about externalities, and then you have to think about how to incentivize renewables through tax credits and carbon pricing. And then transmission is now the moving the electricity. We're seeing now a lot of high voltage transmission, which is electricity transmitted over long distances using high voltage lines to minimize losses. So you have several components of the grid. First off, you have substations, which step up and step down transformers to adjust voltage levels. Second off, transmission lines, high voltage lines that connect generation to distribution networks. So you have a bunch of substations where they use transformers. If you ever hear about the electrical bus, this is what's at a substation. This is where each of the prices are set. And then you have transmission lines that take the electricity long distances between different places and between different distribution networks. So obviously you lose electrical energy to heat during transmission, and there are ways to mitigate that. High voltage direct current has lower line losses, but there are challenges to the direct current, particularly on cost. Congestion, when demand exceeds capacity of transmission lines, prices rise in some regions, space, supply issues. We'll talk specifically about how that works in the third section of this lecture on transmission. And you have infrastructure costs. Build out, maintaining transmission networks requires significant investment. And it's not just that it's costly, it's that there's significant need for political capital and need for support for building out transmission networks. It's just hard to build things. Distribution, delivering electricity to consumers. You have local networks that take electricity from transmission lines and deliver it to homes, businesses, and industries. You have a voltage reduction. Substations reduce the voltage to safer levels for consumer use. This happens at the transformer and the electrical bus. Consumer types, you have residential, consumer, commercial, and industrial. Industrial users have factories and heavy users with specific voltage needs. These are the people who usually have the most control over when they're needed to produce, and they have very specific needs for what their electricity should look like. Businesses, offices, and service industries, they use a little bit of electricity, but they kind of need it to be on for them. And then homes and small scale users, they're not using very much, but there are a lot of them. So technological trends, smart grids, and advanced metering infrastructure are changing how the distribution network works, allowing for more understanding of how different activities affect the production of, or the consumption of electricity. And you're also seeing with advanced metering infrastructure, you're seeing the ability for what are called virtual power plants. This is very big out in Arizona, where you see different small users act as like power plants and act as agents in the grid and are paid for basically turning up their thermostats when it gets hot outside. And then distributed energy resources, you have rooftop solar and home batteries. Home batteries, I'm optimistic about because it makes a lot of sense in the use case. Rooftop solar is a product of low interest rates. I don't really see it as like a long-term solution. So the history of electricity markets in the late 19th century, the birth of electricity. Thomas Edison invented the practical incandescent light bulb. He had really the first modern research lab that was doing some really important work. And then 1882, you had the first power plant. I have a picture of it on my wall. The Pearl Street Station in New York, which was established. And from there, it was just, the rise of the monopolies. Edison's right-hand man, Samuel Insull, realized that utilities could be monopolies. Electricity grids expanded, and vertically integrated monopolies controlled generation, transmission, and distribution. These became very lucrative, expensive, successful companies where prices and access varied widely. And then the public started demanding regulation, and you see a lot of that around the 1930s and after. With the mid-20th century, you see the regulation era, where you see government agencies such as the Federal Power Commission, now the Federal Regulatory Commission, I interned there one summer, beginning to regulate electricity markets. And you see a focus on universal access and affordability through cost-based pricing. Then in the 1970s and 1990s, early 20th century, we saw this rise of monopolies. 20th century, we saw regulation. And then we decided, actually, that regulation was no good. Let's deregulate everything. There were energy crises in the 1970s. A lot of utilities went bankrupt. We'll talk about in a couple lectures now. We'll talk about the economics of nuclear power. We'll say part of why these utilities went bankrupt was because there are large investments in these expensive things like nuclear grids or nuclear energy that really had high fixed costs and cost overruns that bankrupted them. So there was demand for cheaper electricity. People were feeling a lot of the same things they're feeling now. They were like, energy prices are too expensive. Everything is too expensive. We want things to be cheap. And this led to electricity market restructuring to introduce competition. Most prominently, California Grid, CAISO, the Texas Electricity Grid, ERCOT, which we'll talk about really in our last section of the class. We'll talk a lot about ERCOT. And then the PJM interconnection, Pennsylvania, New Jersey, Maryland. NYISO, where we currently are, if you're in New York, or maybe you're taking a break and you're somewhere else. NYISO is also a restructured electricity market, as is ISO New England. And then this stopped in the early 2000s with the California blackouts. You saw PGE, Pacific Gas and Electric, had a lot of problems. I think they went bankrupt a couple times. It was really rough out there. Electricity skyrocketed. Enron, who was the largest employer in Texas at the time, engaged with Arthur Andersen in a lot of fraud. And it was pretty clear at the time, maybe not so clear now, that the wholesale electricity market system was having problems. And so this stopped the deregulation impulse. And now we're stuck with a hybrid system where there's some deregulated markets, some regulated markets. It's an odd system we have where we have these deregulated markets. I shouldn't call them deregulated because actually there are a lot of regulations even in them. We have these less regulated, more decentralized electricity markets, and then we have these very centralized, vertically integrated electricity markets functioning together. And now in the 21st century, we have the modern electricity markets. We have an integration of renewable energy source and demand response programs. We have smart grids and advanced market designs that handle intermittent generation. We have a focus on decarbonization and sustainability, which will define, I think, my career and many of your career. And then next time, we'll finish up with a look at what makes these deregulated electricity markets so special. Thank you, and I hope you have a great day. I am very excited for this portion of the class.